Okay, I'm going to introduce a new concept called automorphisms. You'll recall that we've got a homomorphism phi, and that satisfies the basic rule that 5xy equals 5x phi of y. Well, an automorphism is a special kind of homomorphism. You'll recall that, this is happening quite a lot. You'll recall that phi maps G to H. Well, an automorphism, I'm going to say psi maps G to itself, where psi is two things. First of all, it's a homomorphism, and second, it's a bijection. It's an invertible map. And this places a very, very strong restriction on what kind of maps are admissible. So you'll remember a bijection looks like this. Here's a nice little set. It points, each member of the set points A is mapped to B, because you can go backwards. So we've got lines going from left to right, and we can invert this map. So I'm going to prove something quite peculiar. Well, I'm going to assert it and then I'll prove it. The set of automorphisms of a group is itself a group, which is quite a confusing thing. So I'm going to do that. You'll remember the definitions of a group. Right. The set of automorphisms of a group is itself a group. Well, first of all, you'll recall that a group is an ordered pair of a set and an operation. It might be a little circle or a star, and that's a binary operation. With 1, 2, 3 or 4 axioms, depending upon whether you include closure. So let's just take closure. So phi. So hang on a minute. You've got, if x and y are in the group, then you need the x combined with y is also in the group. That's closure. So we've got that. Secondly, we require that there exists E in the group such that for all x, xe equals ex equals x, so we've got a neutral element, an identity element, and also there exists x minus 1 in G such that x minus 1 equals x minus 1 x equals e, an inverse element, and also x y z equals x y z, associativity. So it needs to be closed, there needs to be a neutral or an identity element, there needs to be an inverse, and it needs to be associative. So what is this operation here that can be applied to automorphisms? Well, I'm going to make the answer completely and utterly obvious to you by writing it in a peculiar notion. If I've got an automorphism, I'm just going to write it as f subscript 1, and this maps G to G. So we might write that f1 of x equals y. And if I've got another automorphism, I'm going to write it as f2, which also maps G to G. And I'm going to specify that f2 of, let's say, z equals p. Just making up letters here. So if I want to combine f1 combined with, in scare quotes, f2, well, it's pretty obvious that this we want a function. We want f3, which also maps g to g. f1 maps g to g, f2 maps g to g, and f3, which is f1 combined in some way, which I haven't really stated yet. So we need to specify f3 of x. We need to know what f3 of x is. We need to specify what this is for all x in the group. Well, it's pretty obvious that we do this. f3 of x is equal to that. So it's, in other words, the group operation is just functional composition. So x goes to f2 of x, which goes to f1 of f1 of x. That's not right, f2 of x. You'll notice I'm putting f1 on the outside and f2 on the inside, just because I feel like it. But lots of people do it the other way around, and you get left-handed and right-handed notations, and it's enough to drive you nuts. But I'm just going to write it like this and I've done with it. Let me write that out in a slightly more formal notion. f1 combined with f2 maps g to g, with f1 combined with f2 of x equals f1 of f2 of x for all x in the group. So what I'm doing here is I am constructing a way of combining two elements of this rather peculiar set here. So what is the set? The set is the set of automorphisms of a group, and if I've got two automorphisms, I'm going to combine them simply by running f1 and then f2. So we better prove that it's a group. So it's closed because the combination or the composition of two, it's closed because f1 combined with f2 is an automorphism. Actually, that's not obvious, is it? So I better prove it. So what do we mean? Well, to be an automorphism, first of all, it's got to be a homomorphism. So we need to verify that f1 combined with f2, need to check, is first of all a homomorphism, and secondly a bijection. Well, that one's obvious because the composition of two bijections is of course a bijection. Is it a homomorphism? Well, what does that mean? Well, let me just write down what a homomorphism is, and then we'll check to see that it's satisfied. f1 combined with f2 of xy equals, we hope, f1 combined with f2 of x, f1 combined with f2 y. All I've done is write out the definition of a homomorphism. Well, we want. This is required to prove. We're trying to show this. Okay, well, let's just evaluate the left-hand side and the right-hand side and check that they're equal. What is the left-hand side? It's f1 of f2 of x, y. Just by definition. That is what this circle means. It means do f2 and then f1. You see why it's odd? It's because you do f2 to it first, because that's in the inner bracket, and then f1. So some people write it out the other way. Now what's that? Well, that's f1 of something. F2 is a homomorphism, remember? So that's f2 of x, f2 of y. Ah, and now we're getting somewhere. So that's equal to, so now I'm going to use the fact that f1 is a homomorphism, and that's f1 of f2 of x f1 of f2 of y. Okay? So this equality is because, which way around is it? That's because this one is f2. This one is using the fact that f2 is a homomorphism, and this line is using the fact that f1 is a homomorphism. Let's have a look at the right hand side and see what we can get from that. Well, we just write out what the definition is. This one is equal to f1 of f2 of x, which is that bit there, composed with f1, f2 of y. And of course all these equalities go backwards. And so we're taking this guy here and unwrapping it to this form here. And I'm taking this guy here and I'm just unwrapping it to this form here. So we've established the truth of this relationship here. So that tells me that f1 composed with f2 is it's an automorphism, because it's a bijection, that's obvious, and now we've established that it's a homomorphism, and if it's a bijection and a homomorphism, then it's an automorphism. So it's closed. So the little circle operation is closed. What else do we need for a group? Neutral. Well, it's pretty obvious what the neutral element is. We need a function f which maps g to g, which behaves like a neutral element. So of course I'm going to call it e, and I'm going to specify that e maps g to g, and I'm going to specify that e of x equals x. So it's the identity function. Brilliant. So the identity function will do. And I'm not even going to prove that that's right, because that's obvious. Inverse. We need the inverse. So f maps g to g. Of course, what I'm going to consider is f to the minus 1, which is the group. It's the functional inverse. You'll recall that if f is an automorphism, then it is invertible, and so I'm just going to invert it. So I'm going to check that it's it's part of the set because it's an automorphism. And does it work? What happens if I compose it like that? What does that function do? Well, it maps x. That's equal to f of f minus 1 of x. Well, that's pretty much the identity element. Yep, that'll do. And of course, if we write it the other way round, well, that's equal to f to minus 1 of f of x equals x. So that's true as well. There's one last rule, which is associativity. So what we've basically got to show is that fgh equals fgh. Well, what do these maps do? They take f of gh, that function there of x equals f of g of h of x. And what does this one do? Let's have a look at this one. That says fgh of x. What does that do? I should be writing these circles in here to mean group composition. I don't have to write them in, but they've all gone from that. What's that one? Well, that is fg of h of x, which by definition is f of g of h of x. So those two things are equal. On the one hand, it's so blindingly obvious that they're equal that I hardly need to state it. But on the other hand, once you start thinking about it, composition of functions is an associative operation is very, very, very far from obvious. It's one of these things, it's like the vase and the two faces, it's like an optical illusion. Sometimes you're thinking about it, you think, well, of course it's associative. And yet, there's something rather slippery about this line of argument here, which I'm finding great difficulty expressing. It is associative, there's no doubt about it, but that's a very, very deep and very, very, very profound statement about mathematics, that functional composition is an associative map. It's very profound indeed. Anyway, for the moment we're just going to ignore it, and we have established the result that I said I would, which is here, which is that, oh dear, the set of automorphisms of a group is itself a group, and I should have said under composition. I didn't say that at the beginning because, well, I had to establish that composition was the right thing to do. But there it is. The set of automorphisms of a group is itself a group. It's called out G. And that's quite a nice little group, and I'm going to stop there.